Hello everyone. Today we will continue discussing our topics in MOSFETs. We discussed before the MOSFET analysis, the DC analysis of our MOSFETs, and we mentioned that DC analysis are very important to identify the operating point of the MOSFET. And we mentioned also one of the MOSFET applications is digital logic, is switches for power, and also amplifiers. So today we are gonna go more in deep and discuss the amplifier application of MOSFET. So let's say, guys, since we learned now MOSFET and JFET, so both of them having more or less similar characteristics. Yeah, the operation is a bit different, the relations are a bit different, but in general we say field effect transistor because JFET and MOSFET both are depending on the field effect of transistor. So let's discuss the basic FET amplifiers, but we mean here the MOSFET one. So the objectives of this new material, we may need more than one class in this material. So we will start today, and according to our progress, we will decide. So the objectives of these materials are investigate the process by which a single transistor circuit can amplify input signal. So we will see the transistor circuits, how this transistor circuit will react with the input signal in order to be amplified. Then we will develop the small signal models of FET linear amplifier and what the meaning of linear amplifiers. So we will discuss this more in deep today. So firstly, we have some basics we need to discuss before of going more in deep in the waveform and amplification. So firstly, a signal. So signal is any waveform. So our voice is a signal, light is a signal, and every signal has a certain waveform. So we can say that a signal contains some type of information. So from the waveform parameters, we can get this information. For instance, sound waves produced speaking human contain the information the person is conveying to another person. These waveforms, these sound waveforms are transmitted by mobile phones and moves even in landline phones or whatever the media of transferring the data. And it is like decoded and coded in order to be heard on the other side. For sure, we need to have some filters, we need to have some amplifiers for these waveforms in order to provide the data in a correct way. So a sound wave is considered as an analog signal. So you know that, guys, we have two different types of signals. We have analog signal and we have digital signal. Digital signal, like what you are learning now in microprocessor systems. So digital is zeros or ones. It can be translated in voltage levels, okay? But by the end, digital logic is either 0 or 1. So any signal transmitted to digital contains only 0 or 1. However, analog signal is different. Analog signal has different values. So the magnitude of an analog signal can take on any value within limits and may vary continuously with time. With limits means with the limit of the data values you have in your system. So if you are dealing with a signal in a circuit of voltage levels from 0 to 10 volt, for instance, so you expect the data to be any value from 0 to 10. But if you have some values more than 10 or less than 0, it will be saturated. It will not be decoded in the waveform, which means now we have some distortion. So in order to change the signal limits, we may need to decrease the gain or increase the gain, or let's say decrease the magnitude or increase the magnitude. So this means multiplied times a gain. And this is nothing but amplification. So amplification means multiplying a signal with a certain gain. Okay. So electronic circuits that process analog signals are called analog circuits. And the same, any signal or any circuit processing digital signals is called digital circuits. And also analog circuit can be referred to as linear circuits or linear amplifiers, which magnifies means multiplies the signal times a certain gain. So magnifies an input signal and produces an output signal whose magnitude is larger and directly proportional to the input signal. Okay. So this is the signal amplification. The term small signal means that we can linearize the AC equivalent circuits. Linearize, what the meaning of linearization, we are gonna discuss more in deep in this part here. So the term linear amplifiers means that we can use superposition. Superposition, I think you learned superposition before in electrical circuits, and we will see what the meaning of using superposition here in our small signal and in linear amplifiers to identify the signal parts and start amplifying a certain signal. Okay, so we have to use superposition here so that the DC analysis and DC and AC analysis of the circuit can be performed separately. So this is the concept of superposition. Superposition, we have in the same waveform, we have part of the waveform DC and another part AC. So we need to separate these parts and start interacting with every part. This can be done or calculated by using superposition, but we need to make some modeling to understand that. Okay. And by the end, after applying the superposition, the total response is going to be the summation of the two individual responses of the DC and AC. Okay. So this is a concept in linear amplifiers. So we will have DC component, we will have AC component. The DC component refers to the part we already discussed before, guys, which is the DC analysis of the circuit. And the AC component will refer to the data or the signal that will be amplified in our circuits. Okay. You know, guys, this is our MOSFET. This is a simple circuit of common source MOSFET. So the source is connected to ground. The drain is connected to a resistor, then to a DC source. This is here the VGS connected to the gate, and this is V drain to source, and we call here, this is V out. Why this is V out? Let's discuss that on our curve here. We could see this curve for sure before, and we already made a lot of DC analysis on this curve. So this is nothing but the ID versus VDS curve at different operating VGS value. And here, you know that this is the, let me have the cursor here. So this is the VDS saturation locus in our characteristic, and it it separates the linear part and the saturation part in our waveform. Next, the pen. Okay, so let's have the pen instead of the laser one. Okay, so here is our locus of VDS saturation. This is the linear region, and we don't work in the linear region in the amplifier as we discussed before. So the linear region is used for the digital logic and for switches application. But here in this saturation region, we use it for the amplification. So this is for the amplifier application. So our target is going to be only in the saturation region for this application. Okay, where is the signal and what is V out? So we already discussed this before, guys. So this is the DC analysis, and we mentioned that you can control the value of VDS and ID by means of RD here, okay? And you can select your load line based on that RD value. And we already had one lab regarding the operating point, and we analyzed the performance and characteristic of the MOSFET based on that load line. So now, if you have an input signal, so I added here now V input, and I still have V output here. So V output from this graph here, guys, or from this circuit is nothing but the volt between this point and ground, which is V drain to source. So this is the output volt, and the input volt is mentioned that this one. Actually, this is AC signal. And we still have here VGSQ. So we have now V input as AC, and we have DC. So we have now like two sources together. And we expect also to have, for the output volt here, we have also DC component and AC component. So if you apply a certain input AC across or with an offset of VGSQ, assume this is the offset of VGSQ here, and the AC will be added to this DC component. So the peak value of the AC will be nothing but VAC peak value plus VGSQ, which is going to be this point here. And the negative amplitude of this AC will be added to VGS again. So this is going to be the negative amplitude. So by the end, this signal here represents the AC plus the DC component. So this is our signal right now on the gate side of this MOSFET. According to this load line, which is already tuned by means of the DC analysis, VDD and RD, and the amount of ID, we will have the reflection of the output on VDSQ like that. Again, here VDSQ is DC component plus AC component. The DC component is the value of VDSQ that we have. So this is the value of the DC component, which is VD S, V capital DS. Take care that this is V small ds. And I'm going to discuss with you now, guys, what's the difference between little letters and capital letters for the symbol or the D or S or whatever we have here. So we will discuss all of that in the coming few slides. So we have now DC component and AC component. So the DC component is nothing but this VDSQ here. And the AC component is the oscillation around these DC components. How much peak we can get here, it depends on the intersection point of the signal here. So it depends on the input signal and the load line. So it will be reflected on the load line, okay? So the load line has a major effect on the gain of the output volt. So we will see what the meaning of the gain of the output or the amplifier according to our discussion today. So by the end, guys, this will be now the amplitude of the output AC signal, okay? And this is the amplitude of the input AC signal. And we have a certain gain. We will discuss how to get this gain in our model today, okay? So this is the concept of having amplifier. So firstly, you need to identify the DC analysis in order to provide the DC component or the Q point. Q point means certain value of ID, certain value of VDS, and a certain VGSQ. Then applying the AC components according to the gain value we have and load line, we will provide the output volt here. Okay, so this is the amplification process. Let's go more in deep and see the difference between the analysis. So regarding AC and DC notations, it's very important, guys. If you have little letter and capital subscript like that, this means it's total instantaneous value. So instantaneous value including all components, DC and AC. What the meaning of instantaneous value including all of components? In order to know that, let's review together the Fourier series. So this is Fourier series. I have a certain function of omega t, f of omega t. It has a DC component and AC component. So within the signal, we have two parts, DC part and AC part. For any waveform, we have DC component and AC component, DC part and AC part. The total function is called the total instantaneous value. Okay. What is the DC value? The DC value means the average value of the waveform. So if you have a waveform f of t like that, and you made the average of this waveform, it will provide you with the DC value, which is f node here in this case. What the symbol of or notation of the DC component? So it's gonna be, guys, capital letter with capital subscript. Okay, so capital letter with capital subscript. So this means DC value of our waveform. What about little letter with little subscript? So little letter with little subscript means the AC component of the instantaneous waveform. So can you see here, guys? This is the AC component of the instantaneous. All of these are the AC components, okay, with different frequencies. So instantaneous value, AC component, it's little letter, but little subscript. So little letter, capital subscript is the total, including the DC as well. But little letter, little subscript means the AC components only, without DC components, okay? Which means the AC response of your waveform. And AC response means the waveform minus the average value. So the AC can be represented by the waveform minus the average value of the waveform. For that, guys, if you are measuring any signal on oscilloscope, you have what's called AC coupling and DC coupling. If you bring the scope to the DC coupling, it will show you the complete waveform. If you select the channel to be AC coupling, so AC coupling, it will subtract the waveform minus the average value or minus the DC components. So we can use the AC coupling in oscilloscopes to see the waveform ripples, which is the AC component of the waveform. Okay. In our analysis today, the AC components represents the AC signal that will be amplified. And the DC component represents the DC biasing analysis or components or parameter that we design in order to identify the operating point, which is the DC analysis we made before. Okay. What about the capital letter little subscript? So capital letter little subscript means the phasor or RMS values of the AC. So capital letter little subscripts means the RMS values or phasor values. Okay. So these are the different forms or notation we have for DC and AC components. Okay. Let's see how can we apply that to our equations and circuits today. So I can say for this signal here, the input volt we have is AC component and DC component. So VGS, little v capital GS, which is the complete instantaneous waveform, will include both the DC component and the AC component. So I can say here, little v capital GS, so this means the AC, but a few minutes, guys, I'm not going to say little and capital, so I'm going to say VGS, and you should know now, according to this notation, this means it's AC, sorry, it means it's total instantaneous, since you have here little v and capital subscript. Okay, so this means the complete instantaneous curve or value. So VGS instantaneous equals capital V capital GSQ, which means the DC component of VGS, plus little v little I, which means the AC component of VGS. And again, VGS or VI are the same, so we are going to refer to GS here as the input signal of our amplifier. So we can say this is VGSQ capital plus little VGS. So this is now the input of our amplifier. What about the current and voltage relation of the MOSFET? You know that in saturation region, ID equals Kn times VGS minus VTN square. So VTN is the threshold volt. If you substitute with VGS from this equation here in this equation, so you will end up with, it's going to be VGSQ, which is the DC component, plus VGS, which is V input, minus V threshold. So we can say, let's have the DC parts together. So VGS and VTN together here. So this is DC, and VGS is the AC signal. So we can say, if this is square here, so let's get the equivalent of this relation. So we can say it's Kn times VGSQ minus VTN square plus 2 times first and times second. So 2 times Kn times VGSQ minus VTN times VGS plus the last square. So Kn times VGS square. What is the DC component here? So the DC component is going to be this part here. It's completely DC. So Kn times VGSQ minus VTN square. So this is a complete DC. And here, this is 2Kn times VGSQ minus VTN times VGS, which means it has DC times AC. And here, this is pure AC. So the first term is the DC or quiescent drain current IDQ. So this is the IDQ part that we have. This is the complete DC part that we have in our analysis. And this is the term that we already used to do in the DC analysis. So this is IDQ. The second term is time varying drain current component that is linearly related to the signal VGS. So it's a part of the current which is depending on VGS. And the third term is proportional to the square of the signal voltage. So this is the analysis of the current. So we have 3 terms now. For sinusoidal input signal, the square term produces undesirable harmonics or nonlinear distortion in the output waveform voltage. So the last term here, guys, is desirable noise. So what should we do? To minimize these harmonics, we require that VGS should be much less compared to 2 VGSQ minus VTN. So the AC component VGS, which is the AC input, should be less than VGSQ minus VTN. So this term has to be much less than this term. So if VGS is much small, so squaring a small value will be very small, which means this can eliminate this part from the equation. So we can assume that this part is neglected since VGS AC is very small. So in this case, guys, we can say that Kn VGS square can be neglected. So this term can be neglected. So we can say now the current, total current has 2 parts. First part, which is the DC component, and second part, which is depending on the AC component. And we are caring now about the AC component. So we can say the AC current is 2 Kn times VGSQ minus VTN times VGS. And the DC component, we already know the DC component, and we use it before in the DC analysis. So now, for AC analysis, we are going to take care of this part. So we have a new term we will define, which is called transconductance. So the transconductance is a transfer coefficient relating output current to input volt. So it's a relation between the output current of the amplifier, which is ID, because ID is output, and the input volt, which is VGS. So I can say now the transconductance is GM, so we can give it a simple. GM, so GM equals ID divide VGS. So ID divide VGS means this term can go in the denominator in the other side. So the relation of the transconductance is 2Kn times VGSQ minus V threshold. This means, guys, that the transconductance depends on Kn and the difference between VGS and VTN. VGSQ minus VTN. So it's mainly depend on DC values now and the conduction factor. Okay. So this is called the transconductance. If I would like to calculate the transconductance at a certain operating point at VGS equals VGSQ, which is constant, so we can say now GM equals 2Kn times VGSQ minus VTN, which is equal to 2 times square root Kn IDQ square. Okay, so this is the relation of the transconductance. Okay. So this term, guys, if we go back one slide, if it is not clear for you, let me show you that from here. So from here, guys, we have I dq, the DC, equals Kn times VGSQ minus VTN square. So from this relation, you can get the relation here, okay, between I dq and Kn and VGS. So just replace this part here, okay? So VGS minus VTN. So this is VGS minus VTN. So we can say here, let's have this term here. So I can say I dq divide Kn equals VGSQ minus VTN square. So I can say now the term VGSQ minus VTN equals root I dq divide Kn. So in the relation here, if you would like to replace this now, so this term can be replaced by root I dq divide Kn. So you have Kn here outside. So Kn can go inside the root. So it would be by then 2 times root Kn I dq. Okay. So this is just a simple form for the transconductance. So you can use whatever relation you need. Okay. So again, the transconductance is nothing but partial ID of the overall AC component by partial VGS of the overall AC, sorry, not AC component, overall the instantaneous curve at a certain condition, which is VGS equals VGSQ equals constant. So this is the condition. And at this case, so the transconductance is 2Kn times VGSQ minus threshold volt, or 2 times root Kn times IDQ. If you draw, and we already draw this characteristic before in our lab, so this is the relation between ID and VGS. You remember that, guys, we identify the value of V threshold in our lab by applying different values of VGS and detect the first current increase. Okay, so we said that this volt is nothing but the V threshold, and the waveform we got in the lab was the same like this one. So this is the characteristic of ID versus VGS. So if this is the input signal here through VGS, so this is gonna be the current, okay, and this means the slope of this curve is representing our transconductance. So this is the value of GM at the operating point, okay? So this is the complete curve of GM, which is partial ID by partial VGS, and the operating point here at the certain value of VGS and IDQ, or the Q point, is nothing but the value of transconductance that we have right here. Okay. If we would like to analyze this transconductance, you will find that transconductance depends on two or one important parameter, which is Kn, the conduction parameter. And you know that the conduction parameter depends on the die of our MOSFET, so the channel dimensions, which is depending on the width to length ratio, so W divide L ratio of our die of our channel. So if you would like to have more transconductance, you need to have more width to length ratio, or more conduction factor or conduction parameter. Okay. Let's solve one example here. So in this example, consider an N-channel MOSFET with parameter VTN, threshold volt equals 0.4 volt, and Kn prime equals 100 microampere per V square, and the width to length ratio is 25. Assume that the current IDQ is 0.4 milliampere. So what do we need to do here? We need to calculate the transconductance. So the relation is very straightforward, guys. So GM equals 2 square root Kn IDQ. IDQ is given. Kn, we can calculate Kn. So we have W divide L, and we have Kn prime. So we can say now Kn is nothing but Kn prime divide 2 times W divide L. So we discussed this relation before in the early beginning of discussion of the MOSFET construction and operation. So 0.1 divide 2 times 25. This is going to be our conduction parameter, 1.25 milliampere per V square. Now, assuming the transistor bias in the saturation region, this is 100% because it's working now in the amplification, and we don't care about the transconductance anywhere. So we care about this transconductance in the application of the amplifier. Okay, so the GM now can be calculated as 2 root Kn times IDQ. So 1.25 times 0.4 under root times 2. So this would be 1.41 milliampere per volt. So this is the transconductance we have. Okay. So we have a comment here from the textbook. The value of the transconductance can be increased by increasing the WL ratio and also increasing the quiescent drain current. So drain current for sure will affect the amplification and the transconductance value. We will see later on, guys, the amplification gain. Now, we understood what the meaning of transconductance. We will use it now in our circuit. We need to make equivalent circuit for our MOSFET. So the MOSFET, you know that it has drain plate, it has source plate, it has gate plate, it has the isolation material inside, it has the P and N semiconductor materials, and so on. So this is just a simple for our MOSFET. We need to convert this to what's called the small signal model. Small signal model, guys, it means convert this to equivalent circuit. Equivalent circuit means passive parameters like RLC. It means current sources, voltage sources. So this is the equivalent circuit. So we need to have an AC equivalent circuit. AC, why? Because we are going to represent this for the amplifier. So we need to have AC analysis here. We need to make the AC analysis. We already learned how to make DC analysis for the MOSFET before, and we were using two different sets of equations, or two equations. One equation from the circuit, like for instance, VDD equals IDRD plus VDS. So this is the circuit equation, and the other equation is the MOSFET equation. Okay, but we didn't go inside the MOSFET itself in the DC analysis because we don't need to go inside. We already represent the inside parameters by means of the ID versus VDS equation. For the AC analysis, we need to have a similar thing, but we are gonna make or provide equivalent circuit for the MOSFET in the AC analysis. So let's see how can we do that. So firstly, we agree that VDS equals the output. So the output of our gain or of our amplifier is gonna be the DS volt. Again, little v, capital DS means the complete instantaneous waveform or the complete instantaneous signal. So we can say now VDS equals V out equals VDD minus IDRD. This is in terms of the AC or DC circuit, whatever. So this is here from the circuit. And you know that ID has two components, IDQ, which is the DC component, and ID, which is the AC component. So we can say V out equals VDD minus, let's substitute now with ID here in our equation. So this is going to be ID DC value and ID AC value times RD. So you will end up with this equation, which is the DC value we used to use before in the DC analysis, minus the AC current times RD. Okay, so this is the complete analysis or the instantaneous complete signal. So we can say that the output volt is also combination of DC and AC. This part is DC and this part is AC. So if I would like to say now what is the output AC value, I can say it's minus ID times RD. This is simply the output volt of our amplifier. Okay, and it's equals to the drain to source, because drain to source, the AC component of drain to source, because it's already connected in parallel with it. So this is VDS, and the output is also the volt between this terminal and ground. So it's equivalent to the the AC component of VDS. Since we are interacting only with AC now, we don't care about the DC. So let's use superposition. And if we are using superposition, we will remove all DC sources from the circuit. So here we have RD connected to VDD, and connected to VDD means we have here a DC component, a DC source called the VDD connected to ground. So this is VDD. And if you are make superposition, so VDD or DC sources will be removed from the circuit. So this would be connected to ground now. So we can say between V out and the ground, we have resistance RD. So this is the resistance RD between V out and the ground. And here in the gate side of the MOSFET, we have AC component and DC component again. Remove the DC component by superposition, so we will have only the AC. So this now represents our circuit. But this is the complete circuit, not the MOSFET circuit. Okay? So the complete circuit is we have resistance RD, we have ID flowing from the drain terminal to source terminal of the MOSFET, and we have the input connected to VGS. So this is the amplifier AC circuit, but not the MOSFET AC circuit. So we need to make a model for the MOSFET. So let's see, guys, how can we make a model for our MOSFET and then replace this part of the circuit by the equivalent circuit of the MOSFET and return it back here in this circuit. So this would be the equivalent circuit now. Okay. The equivalent circuit of the MOSFET, we will call it small signal equivalent circuit. Small signal equivalent circuit. How can we do that? So let's say now this is our MOSFET. The drain current is going to flow here, and this is the drain to source, and this is the gate to source. So the gate to source can be represented by input volt, and here you don't have physical connection between the gate and the other parts of the element, so this would be open circuit here. And then from the drain to source, you have the ID input here. So you can represent something here for the current ID. We just got a relation that ID equals GM times VGS. So we just derive the equation of the transconductance. So the AC component, the AC component of the drain current equals GM times VGS. So this is the AC component, and this is the RMS component or phasor component. So we can say now, since ID is a function of VGS, so we can say this can be considered as a current source, but depends on a voltage magnitude. So this is voltage dependent current source. So we can represent this by a dependent current source, and the equation depends on the voltage magnitude, which is GM times VGS. And the direction of this current source, for sure, it's going to be the same direction of the drain current. So this is the shape now of our small signal MOSFET. Or let's say simplified small signal MOSFET. Why it's simplified? We are going to discuss this in the next slide. So let's say now we will replace our MOSFET by this simple model. But if we need to consider the accurate model, let's see what we have. You remember before, guys, we mentioned that this is the exact characteristic of the MOSFET if we consider the slope of our curve. So this is the linear region. Here we have the saturation, and we said that the saturation is not like constant value. If you extend this line to minus value, it will be interact at V avalanche, and you have here a factor called lambda. And we discussed this before in our classes. So this is the exact ID V DS characteristic. So it has certain slope. And we mentioned that this slope depends on a value called lambda. Okay. And this is the relation. It was 1 plus lambda VDS. So if you would like to get the exact relation, what should we do now? I'd like to get the value of output resistance. How can I get the output resistance? So the output resistance can be obtained by means of differentiating the ID versus VDS. So if you make the differentiation of this equation, approximated value is going to be just lambda VDS. So I'm making differentiation for ID to VDS. Okay. So by the end, lambda VDS will be the remainder one. So it's going to be lambda only times IDQ. So we can say R out equals 1 over lambda IDQ. So this is the value of the output resistance. This is the value of the output resistance. So R out equals lambda times IDQ. So since this is the output resistance, so it should be connected in parallel with our MOSFET like that. Okay, before of the ID. So this is gonna be now the exact, or let's say expanded small signal model. So this is called expanded small signal equivalent circuit, including the output resistance for N-channel MOSFET transistor. Now, let's add this expanded small signal circuit to the circuit here instead of the MOSFET itself. So this is going to be now the complete small signal equivalent circuit. So the complete small signal equivalent circuit of a common source N-channel MOSFET is V input as AC. You have here isolation. You have the current source, GM times VGS. You have the output resistance, which is lambda IDQ inverse. And you have here the RD resistor, and the output here is going to be our V output or VDS. So this is now the equivalent circuit of our common source amplifier. Here, take care that these values represent RMS or phasor values. Okay, so this is VGS RMS value. This is VDS RMS value. This is V input RMS value. RMS values means it's the RMS of the AC component. Okay, so again, this is AC small signal equivalent circuit of the N-channel MOSFET using the common source configuration. So we can summarize our relations here in this slide now, guys. So we have R out equals inverse lambda IDQ, where IDQ is the DC value. GM transconductance equals 2Kn times VGSQ minus VTN, or 2 times root Kn IDQ. And VGS and ID are the DC values. We make it in the DC analysis. Now we can find a gain for our circuit or our amplifier. So the gain means output volt divide input volt. So we're amplifying a voltage signal. How can I get the output volt here? So I can say the voltage gain equals V output divide V input. So it's VDS divide VGS, and take care, these are the DC values. Sorry, these are the AC values. So I can say this is current, and this current is going to flow here and will be distributed between these two resistors. So if I get the combination of these two resistors, the parallel of RO and RD, and multiply this times this current, this would give me the volt, but in negative sign, because the current is going to make a polarity positive, negative like that. So it's opposite to the output required volt. So I can say now, in case of neglecting RD, if there's no RD in the circuit, so we can say that the gain is going to be minus JM VGS RO, which is the voltage drop across RO if RD is not exist in the circuit, divide the input voltage VGS. Okay, so you have here VGS and here VGS. This will be omitted together, so it's gonna be minus GM R out. So this is the voltage gain if the RD is neglected. If RD is not neglected, so you can get the combination of R out parallel RD and the output, the voltage gain is gonna be minus GM times the parallel combination of R out and RD. So this is called the voltage gain of our amplifier. Let's end with this example today. So in this example, guys, we need to get the voltage gain. So for the circuit we have in figure, so it's the regular common source MOSFET, N-channel MOSFET. So it's required to get the voltage gain if VGSQ is 2.12, VDD is 5 volt, RD is 2.5 kilo ohm, and assume the transistor parameters VTN equals 1 volt, Kn equals 0.8 volt, and lambda equals 0.02 volt minus 1, and assume the transistor is biased in the saturation region. So what we need to do is we need to get a V, so it's nothing but minus GM times R out parallel RD. GM is the transconductance, R out is 1 over lambda ID, and RD is given. So let's substitute in the relations here. So firstly, you know that IDQ equals Kn times VGS minus VTN. So Kn is given 0.8, VGS equals 2.12, and VTN is 1. So substitute and get the value of IDQ. So this is IDQ. VDS from the DC analysis equals VDD minus IDQ RD. So substitute in the relation and get the value of VDSQ. So we got now VDSQ, we got IDQ. So we are ready to start in the AC analysis. Start with GM, 2Kn times VGSQ minus VTN. So this is the value of GM. R out is lambda IDQ inverse. So 0.02 times 1 to power minus 1. So it's 50 kilo ohm. Then substitute in the relation. So here he calculated V out alone and then he divided over VGS. Or sorry, he just wrote a relation. So he substituted in the relation as we mentioned, minus GM times R out parallel RD. So GM is 1.79, R out is 50 kilo ohm, RD is given 2.5 kilo ohm. So the total gain is minus 0.426. So this means, guys, when you apply a signal to this circuit, it will be amplified times 4.26, but take care, it will be inverse. And this is why we use cascaded configuration. So you can use cascaded configuration and reverse the gain. Actually, this is one of the advantages of the cascaded configuration or multi-stage configuration we mentioned before. So this will help to has a positive gain and increase the gain at the same time. So you can make more or multiplication of two gains in order to get higher amplitudes. Okay. So to summarize our discussion today, how to solve the MOSFET in AC analysis. Firstly, since you are dealing with linear amplifiers, superposition applies, which means that we can perform the DC analysis and AC analysis separately. So make the DC analysis firstly to obtain IDQ and VDSQ, then replace each element in the circuit with its small signal model, substitute in the small signal model that we used in our circuit, analyze the small signal equivalent circuit, setting the DC components equal to 0 to produce the response to the circuit to the time varying input signals only. So these are the steps now, guys. Start firstly with the DC, calculate the parameters of the AC that we have, the transconductance, the output resistance, and substitute in the relation that we provide from the AC analysis. Okay, so this is a complete analysis for the common source amplifier. Next class, we will continue solving some other problems on P-channel MOSFET and discuss different amplifier circuits. Thank you so much and have a good day.